Okay, so welcome to AE430 Controls. Today we're going to do a little example about taking a block diagram that's phase variable block, in phase variable form, by the way, but a basic block diagram, and turning it into a state space. So this block diagram, as you can see, is only integrators, sum blocks, and gains. So that makes it a little easy right off the bat to figure out how to solve it. But what you want to do is, when you're looking at these, you want to look at them and try to find the x dot locations. So if you take an integration and you get x3, then what you had to integrate was x3 dot. And you do this for all these integrator blocks. So x2, this would actually be x2 dot, and then x1 would actually be x1 dot back here. So you take the integral of x1 dot, it's equal to x1 output right here. And then you have y coming out over here. So that's what you do first of all to define that. But then you go on and you try to define each one of these x1, 2, and 3 dots, each one of these dots, which is actually pretty easy because you can see that x1 dot is equal to x2 right here because it's directly equal to x2 and there's nothing else coming in, just the output of x2 is going in x1 dot. Then x2 dot is equal to negative 4x1 minus 3x2 plus x3. And the reason that is if you're looking at x2 dot, you have a summing junction, so all the stuff summed together. You have 4 coming back here. You have x1, x1's going up here, multiplied by 4, but it's a negative coming back here, and then it's coming into a negative, so it's a negative 4. Or you can just say it's pointed backwards, so it's a negative 4, basically. That's what you can kind of see. It's pointed this direction, so it's a negative 4. So negative 4 times x1, and then you've got 3 coming back here, going in, and then you've got a negative 3 times x2, and then you've got an x3 coming in right here. So x3 coming into this summing junction, and it's positive. So it's mainly the summing junction, but you can also say if it's pointed backwards, it's probably going to be negative, just because of the way these gain blocks are. Okay, and then moving on to x dot 3. X dot 3 is equal to negative 6x2 plus u. And you can see that right here, because you've got 6 times x2 coming in, negative, and the u coming in is equal to x3 dot, right there. So pretty easy. And then y is equal to x1 plus x2 plus 2 times 3. Let me make sure I get that right. Yes. 2 times 3. 2 times 3. I'm sure I feel like I'm messing that up. Look at it right here. So y, you got x2 coming in times 1. Okay, good. Then you've got x3 times 2. x3, sorry. Not 2 times 3, it's x3. I was misreading my notes. Times x3, and then you've got x1 coming in right here, positive. And then you get y. So there you go. There's your y. All defined as nice little differential equations. So from there, it's really easy to set up the state space because you just go, again, let me lay this out correctly for you. So you've got x dot 1, x dot 2, x dot 3, just like this, is equal to, when you're setting up your state space, what I like to do is kind of put x1, x2, x3 in the matrix so you know what's going on. Then x1, x2, x3, 3 align with the rows. So if you're doing the x1 row, you use x1, you have 0 for x1, you have 1 x2, you have 0 x3, and then, actually I missed one little part here, times x bar, I'm just going to call it x bar, which is kind of a numerous notation. You can do x1, x2, x3 here, but I'm just going to do x bar because it's kind of a useless piece of information. Plus, whatever the vector u is going to be. So there's no u associated with x1, so it's going to be 0. And then for x2, we've got a negative 4, x1, a negative 3, x2, a 1, x3, and nothing for u again. So then going on to x3, we have nothing for x1, we have negative 6 for x2, nothing for x3, and then 1 u. So there you go, just like that. And that's your upper state space. And then if you go down here and you get the y vector, just like this, x bar plus 0u. This is almost always 0 over here on the bottom in the output part of the state space representation. So going on here, so y here in this matrix, y is equal to 1x1, 1x2, and 2x3. And that is your state space representation right there. So you're done. Pretty quick and easy once you kind of get practiced up with it. But once you have gains, variables, and summing junctions, it's pretty easy to kind of define the matrix as differential equations and put it right into state space. And if you're really good, you can almost see the state space from this if you're really well acquainted with phase variable form. But that's a little farther than we want to go.